Earth, that big, beautiful ball we call home. Only lately we've treated it less like a home and more like a motel room we've trashed on the last leg of a punk rock tour. Oceans are rising, ice caps are melting, forests are burning, and coral reefs are dying, which all adds up to a situation that climate scientists call really bad. And unless we act fast, they agree it could become really, really bad. Like, irreversibly bad. So what are we going to do about it? Well, it's going to take all of us working together. Policymakers, businesses, and individuals. It's also going to take entirely new ways of doing things, which is what this show is all about. Scientific breakthroughs and new technologies that can be a big part of the solution. We're going to see these things in action and learn how cutting-edge simulation is used to eliminate guesswork, speed up research time, and lower the costs of the next big breakthrough. To take a leap of certainty, if you will. And we'll talk to the scientists, the engineers, and the innovators who are making it all happen. Though not for too long, because they have far more important things to do. Like literally the most important thing to do, which is saving the planet. This is Earth Rescue. Any look at climate change starts with energy. We use it to power nearly every aspect of our lives, our homes, and our businesses. Traditionally, we burn fossil fuels to generate that energy, which puts greenhouse gases into the atmosphere, heating the planet. The solution is renewables, but how do we scale up our energy from wind, solar, and others while reducing our needs? Some of the greatest minds alive are hard at work on those answers, and they're using the predictive power of ANSYS simulation to show them what's possible. But before we take a look at some of the solutions, we need to understand the problem. What is the current state of the world's energy needs?
In 2020, the total energy production in the world was about 600 exajoules. 1 exajoule is the number 1 followed by 18 zeros. 600 exajoules is equivalent to about 10,000 earthquakes of the magnitude 8 on the Richter scale. To put things in perspective.
I mean, that is a huge amount of energy. It's mind-boggling. 18 zero, like I've never heard that number before. Most of that's coming from fossil fuels, but how far have we got to go? How much is coming from renewables?
Currently, only about 25% of our total energy needs come from renewable energy. The rest comes from fossil fuel. So clearly, one of the challenges with renewable energy is how to efficiently scale up the production from renewable sources at the way that's also cost efficient.
So how exactly is simulation used, perhaps in renewable energy?
Simulation helps us with designing more efficient equipment. It also gives us insight into nitty-gritty details of the physics behind what's happening, right? And also it can help us speed up coming up with those better, more efficient design faster.
And presumably also making them, safer and cheaper?
For sure.
What are some of the challenges involved in getting that 25% to 100%?
Yes, there's lots of challenges going on, like in terms of how do we produce energy efficiently. Some of the other challenges are also how do we store that renewable energy. Because one of the issues with renewable energy is that it's very intermittent, right? Solar we can produce based on the time of the day and also based on the weather.
So how do we store renewable energy once it's captured? We could just put it in a battery, but is there a better way? Let's hear what engineers at Amber Kinetics are doing to solve that problem.
Yeah, my name is Kyle Geiser, and I am a mechanical engineer for Amber Kinetics, which is a flywheel energy storage company.
Awesome. So tell me, what is flywheel energy storage?
A flywheel is basically a mechanical battery that operates using kinetic energy. If I were to rotate this, I'm actually storing energy kinetically. The faster I spin it, then the more energy I'm storing. And also, the more massive the ball at the end, then the more energy I'm storing as well. In this case, it's about 5,000 pounds of steel spinning at thousands and thousands of RPM. In order to reduce losses, we operate the flywheel in a vacuum, and that reduces any drag losses. And we also magnetically levitate the rotor as it's rotating in order to reduce any other kind of friction losses.
so science fiction. I love it. So what is the advantage of storing energy this way over using a regular battery?
Maybe you have a phone and you understand how the battery starts to lose charge over time. With the flywheel, the capacity of the storage is exactly the same on day one as it is 30 years later. So at the end of a flywheel's life, you have this very high quality steel that has value, and you can then recycle that. And that is in stark contrast to a battery, where at the end of its life, you are wondering what to do with all these chemicals.
What is that energy used for, and who's using it at the moment?
In the case of utilities, they're going to be using flywheels as a way of storing energy to solve the intermittency issue that solar and wind naturally have. We have customers who are using flywheels and putting them right next to their solar farm. It's local energy storage option. The electricity can be generated locally as well. And then you can discharge that flywheel later on whenever you need it.
So Kyle, it strikes me that having these big spinning pieces of metal could be potentially dangerous, and there's a lot of moving parts, or there's one big moving part rather, and there's a lot of potential to go wrong. So how do you ensure that your design doesn't go wrong?
So the short answer is that we do a lot of simulation and a lot of testing to validate that simulation. So here on my computer, we actually have an example of an ANSYS simulation. And so if I were to show and run the simulation for you, it's at rest. Now the rotor grows, and it goes back down to 0 speed. And so it's going to continue to cycle in this simulation back and forth. And what you see is when it grows, there's a red spot in the middle. And that red spot is showing the high peak area of stress. Amazingly, this large chunk of steel actually grows about 2 millimeters on the diameter, and it actually shrinks in the center by about 1 millimeter. Because it's storing that much energy, it's actually changing shape as it's spinning up and going back down. So as you spin it up, the faster you go and the more massive the object, the more energy you can store. But actually a question for you, Rosh, what's the limitation? Like, what happens if I just go faster and faster and faster?
Well, eventually I imagine the rope would snap.
Yeah, absolutely. So you can't just go infinitely faster or have an infinitely more massive object. There are fundamental limitations in terms of the material. And so that is something that we intentionally need to design around and make sure that that we understand very well the stresses within the rotor, and that we're not operating above that. Those ANSYS simulations give us a lot of insight into potential issues in the design, and we can catch those things early on before we even have to cut any metal to do testing.
So we've just seen a better way of storing energy once we have it, but finding a reliable, abundant and accessible source is another matter. We can't just plug into the earth and generate electricity, or can we? Let's head to Tennessee to speak with the CEO of Quaise Energy.
Geothermal energy, at its essence, is thermal energy from the planet. It's one of the oldest forms of energy. I mean, you go back in history and you see the Roman baths, for example, people exploiting the hot water coming from down below for all kinds of uses. But the geothermal we are trying to unlock has the possibility to become one of the key workhorses of the energy transition. Geothermal is very versatile. It provides heat, and you can convert that heat to electricity. So we can repower power plants, we can use the heat for industrial processes, we can use the heat for residential heating, we can use the heat for agriculture. Drill deep enough, you can actually do any of those things no matter where you are. You don't have fuels, you don't have waste. It's literally right down below. You extract it, you use it, and that's it. You have a power plant that runs on a source of energy that's basically going to last the age of the planet, billions of years, and it radically changes what you can do with energy. And more importantly, it's clean energy. We like to think of geothermal providing 50% of the energy needs of civilization as we go forward in the next not only 10 to 20, 30 years, but the next 2 centuries. The way ours works is we don't change anything for the first part. We're going to drill conventionally, but once we're there, we have to use energy-based systems. And Our drilling system, we like to call it millimeter wave drilling system, does exactly that. It's an energy-based method to vaporize rocks at great depths to unlock that vast source of thermal energy.
You've mentioned how you vaporize it, and to me that sounds basically like magic. Like, how are you doing that?
Envision the following. You have a hole in the ground, you have a drilling rig on the surface, and in that hole, you put a metallic pipe. Inside that metallic pipe, you're going to inject two things. The millimeter waves from the surface, you're not gonna put the millimeter wave source down the hole, you're gonna keep it on the surface, and you're going to inject a gas. It could be air, it could be nitrogen, it could be argon. The waves and the gas transfer through the pipe all the way down to the bottom of the hole. When they get to the bottom of the hole, they heat up, the waves heat up the rock, they vaporize the rock.
It sounds almost too good to be true, this idea that this energy is literally everywhere. So I'm kind of looking like, what's the catch?
The catch is that nobody can do it economically, and I think that perhaps is the most important aspect of our millimeter wave drilling system, is that we're developing a system that will allow us to tap this energy source, no matter where you are in the world, at cost parity with the most competitive renewables. And the gas then picks up those vapors and literally blows them out of the hole. That's it. But nobody, until Quaise came about, put all of those things together in that way. And that gives us a very robust and very simple way to drill very, very deep.
So how did you figure it all out? What was the process to get to where you are now?
Simulation is key to this, right? So very early on, as we were trying to convince ourselves, and then our first investors, our first backers, we did a lot of simulation. How much millimeter wave energy do we put into the hole? How much gas do we put into the hole? How much standoff between the waveguide, the pipe, and the bottom of the hole do we need to have? How do you actually calculate all of these things before you actually do them? So simulation is a workhorse for everything we do.
Together, we've looked at new energy sources, storage, and seen how simulation software, like the kind developed by ANSYS, gives engineers and designers the ability to explore and predict how our products will work or won't work in the future. I don't know about you, but I'm feeling slightly more hopeful about the planet's prospects, though obviously we can't get complacent. Next time, we'll be looking at one of the biggest contributors to greenhouse gas emissions, transportation. But until then, thanks for watching.